In this lesson, I'd like to introduce you to some circuit analysis techniques known as Kirchhoff's rules or Kirchhoff's laws. They're named after Gustav Kirchhoff, and you don't need to know anything about his history or biography. I'm telling you that it is a person's name because in the past I have had students ask me if Kirchhoff is a technical term or some kind of unit of measure or something like that, and it's not. Gustav Kirchhoff developed these rules, which are really a way of looking at conservation of charge and a way of looking at conservation of energy specific to circuit analysis, and they become really useful. The first of them that we'll talk about is Kirchhoff's junction rule. Now, a junction is an intersection of wires. So for example, we have this black wire, this black wire, this black wire, and at any junction of wires, the sum of the currents entering the junction has to equal the sum of currents leaving the junction. It's just telling you that at this intersection, charge can't be created or destroyed. Every electron that goes in must come out. This becomes really useful when you know some of the current values in a circuit and you're trying to figure out the other current values in a circuit. The second of Kirchhoff's rules is called Kirchhoff's loop rule. That tells us that the sum of changes in potential around a closed loop must be zero. And we actually talked about this in the previous video already. As it says here, the potential that is provided by a voltage source must then be dropped by various components, these resistors, so that a full circuit all the way around includes a voltage supplied and a voltage dropped, more dropped, more dropped, and we're back to where we started. So the total added and taken away must equal zero. Notice this script E is being used for the voltage provided, and it's also sort of a script E on the drawing here by the battery. The reason for that is that the script E stands for electromotive force, which is not an actual force, but we will be talking about electromotive force or EMF because it is the theoretical potential of your voltage source in any circuit. The difference between the theoretical voltage and the measured voltage or terminal voltage is due to the internal resistance in any voltage source. Every real-life voltage source has some amount of internal resistance, and it sometimes gets drawn on the pictures right next to the battery symbol like it's a separate resistor, but it's not. That just represents that that the voltage source itself is not a perfect conductor. It has some resistance in it. Terminal voltage is the actual amount of voltage provided to your circuit. We don't always talk about EMF when we're doing circuit analysis. Many times we'll just talk about the provided voltage or terminal voltage for a source. As it says on the slide, the terminal voltage does equal the EMF when no current is flowing. This equation will tell you that if current is zero, then current times the lowercase r is zero. Lowercase r represents the resistance in the voltage source, the internal resistance. And in that case, EMF does equal the terminal voltage. But when the battery is actually placed into a circuit and current is flowing, then the EMF is just theoretical and the terminal voltage is the part you would actually care about. Many questions in circuit analysis ignore the idea of EMF and ignore the idea of internal resistance. And if you are not explicitly asked about those two concepts, then it's a simplified situation and you shouldn't bring them up. It becomes one of those things where the battery's stated voltage is assumed to be the actual measured terminal voltage, and we don't pay attention to what we know is really going on inside of the battery for that question. So only bring it up if it's asked directly. We will practice some problems in class that will let you have an opportunity to use Kirchhoff's rules and see what it is that they're very useful for in conjunction with Ohm's law to do some analysis of some circuits.